Going. Does that sound good?
And we're recording.
Continue. Okay, so we're going to be getting recorded here. So let me just say very quickly, we did this last week, and I didn't say who I was. So the video got posted to YouTube, and then I'm just some random person giving an introduction. So maybe I should just say my name is Michael Zephyr, and I'm an associate professor in the Faculty of Business and Economics at the University of Melbourne. And this is a talk kind of organized by or through the Quantitative Methods Network, or QMNet, which we have here at the University of Melbourne with about 200 members. And if you want to join QMNet, just send me an email. It's at mzyphur@unimelb.edu.au, and I can help you do that. So we're really excited today. We've got Marina Meila. Is that how you say your last name? Okay, great. Here to speak with us, and she's a professor of statistics at the University of Washington, but you hold cross appointments in computer science and engineering, as well as a few other places. You got your master's degree in electrical engineering from the Polytechnic Uni of Bucharest, and a PhD in computer science and electrical engineering from MIT. And you've held appointments at the Bucharest Research Institute for Computer Technology, the Polytechnic University of Bucharest, and the Robotics Institute of Carnegie Mellon University. And your interest is in geometric and combinatorial underpinnings of statistical learning. And your past work encompasses the foundations of clustering, network analysis, graphical models, statistical models on finite groups that describe preferences, algorithms, and scalable computing. And today what we're going to hear about, which is really exciting, is some pioneering work in metric manifold learning, which augments embeddings produced by a manifold learning algorithm with an estimate of the local departure from isometry or isometry in the form of the push-forward Riemannian metric. And so you've got some really exciting work in this area, and yeah, we're just so pleased that you're willing to do this, and thank you as well to Sheridan, given how late it is for you and just the logistics involved. Thank you so much. Let me hand it over to you, Marina, and thanks.
Thank you very much, Michael, and thank you everyone who is attending. Instead of enjoying the nice weather and ability to go outside, which we don't have here completely. It's a pleasure for me, and the difference in time doesn't matter. We are all in the world of, in the nonlinear world of manifolds. I will also take advantage of Michael being here to ask him occasionally whether, for instance, whether the previous talk covered something like manifold learning algorithms.
It did a little bit. So it was kind of a high-level description or overview of some very specific techniques applied in the kind of biomedical context. But to the extent that manifold learning means, for example, dimensionality reduction, nonlinear dimensionality reduction, then it did cover a bit of that, yeah.
All right, so before we get there, but we'll get there very soon, I want to introduce my group and a few students who are currently working on these topics. The last one is Sheridan Grant, who is hosting the meeting, and you will meet the others as we get to their research. In my group, we are interested in learning from data that is not, that even though it's vector, is not in a Euclidean, it's not in a vector space, but in a more complicated spaces. For instance, what I'm going to talk about today is data that is on nonlinear low-dimensional structures in high-dimensional space, which are called manifolds. But we also talk about work on graphs, on ranking, on clustering, and all sorts of other interesting combinatorial data. We do algorithms, we do theory, and we also very much appreciate contributions and inspirations from practical problems, which are a constant source of ideas and of motivation for us. And I hope that this talk will also convince you that all three are necessary. The second preamble is that everything that I'm going to describe, you can do too immediately, because our software MegaMan is in Python. And if you know how to use scikit-learn, the implementers, I being one and the rest of my group being others, took care to have an interface that is identical, the API is identical to scikit-learn in as much as it's possible. The difference being that inside our method, the computation engine is much more optimized so that we can use, do whatever scikit-learn does and much more on very large data. So we can actually effectively, this is a data set of 3 millions. This is a data set that you'll encounter on the next slide probably, or very soon. So you can do all that. Also, all the theoretical, the cutting edge theory that we read about or that we create, it's implemented here. So you're going to have the state of the art in theory with the, perhaps not state of the art in computation, but pretty effective computation. So after introducing manifold learning, my talk will have 3 parts, with the last part being the dessert, so you can pick and choose. One is about the algorithms, the middle of the talk is metric manifold learning, and the last will be various topics which partly could be thought of as applications of metric manifold learning, but partly would be seen as things that we need to do. If by we meaning people who want to do manifold learning. So manifold learning is a form of nonlinear dimension reduction. And all nonlinear dimension reduction problems assume that the data is in high dimensions, but that it can be described well by a small number of parameters. So in this slide, you see a toy data set. These are real images, and I hope you can see what they are in this in the Zoom format. These are images of a face. It's the same face, it's a sculpture. And the 2 coordinates that describe this data are the rotations of the head. Left, right, along the horizontal axis, and up, down, along the vertical axis. So this reduces the dimension of the data, which is 64 by times 64. So that's 2 to the 12th, just 2. Such a dimension reduction is very handy if we want to save space and saves computation, because basically many machine learning algorithms depend on the dimension of the input data. But this is not the main goal. We now have enough memory and we probably have enough computing power to deal with the high dimensional data. The main reason why a scientist would want to do manifold learning is to understand the data. Because manifold learning is aimed to preserve the large scale features, preserve the global features, and suppress the fine scale features. And in some sense, by suppressing the fine scale, which is the only thing that we can see if we look at the data in high dimension, the raw data, we are discovering what these large scale features are, and this could be called science, if done right. And here are some real examples that my group has worked with. This data set has spectra of galaxies, and these spectra, this is one of them, are in more than 3,000 dimensions. We have 2/3 of a million of them, and this is how they are mapped from the 3,000 dimensions to 3 dimensions. I must say that there are really even more spectra there if we need it. This is done by Megaman, and you can already see that not much information is lost by this this mapping to 3 dimensions. However, a lot of insights are gained that we couldn't have gained otherwise. This is another data set and example of application, and this is actually even more interesting, I hope, for the audience here, because this is a simulation, and it's a simulation of the positions of the 21 atoms of the aspirin molecule. A molecule is not fixed and is not rigid. The atoms vibrate. And these vibrations are small movements. However, during the vibrations, some parts of the molecule, like this group or this group, rotate around there with respect to the other functional groups. And this is why when we embed the data in low dimensions, we see these tori and rings. Whereas the data, the original data is 63-dimensional data that looks like this woolly thing. So essentially we take this wool and we unravel it and we get these nice structures that, that actually correspond to what the scientists know that the molecule is doing. I want to say that there's another interesting feature in this particular data set, and this is clustering. Yes, I'm not going to explain much now, unfortunately, but this is the first eigenvector of the Laplacian matrix. And at this point, I haven't said anything about the Laplacian. I haven't defined it. So if you happen to be familiar with Laplacian eigenmaps or diffusion maps, this is the first, or with spectral clustering. Manifold learning in this case, if it's used with Laplacian eigenmaps, can also do spectral clustering. And in particular, this data set has two clusters. And the first eigenvector is this perfect step function that indicates what the clusters are. So without doing anything but trying to embed the data, we also discovered that there are two clusters. And what you see, the nice circular structures are the structures in the two clusters. There is another thing that is interesting to observe in this picture. And that is that to obtain a faithful embedding, I'm going to use the word embedding, and in fact, I'm going to write it here. Yes. Embedding means taking data from high dimensions and putting it in a real space of lower dimension. Yeah. So to obtain an embedding of this torus, because it is a torus, although this torus has only 2 dimensions, it's a 2-dimensional surface, we need 1 dimension more, we need 3 dimensions. And that's true, everybody knows that one cannot embed one cannot make a correct map of the globe. All horizontal, all 2-dimensional maps distort distances, angles, or various other properties of geography. This is true for almost every other manifold. So this torus needs more dimensions than 2 to be embedded in. And so I'm going to take advantage of this picture to also give some definitions that you are going to see later as well. This torus, as I said, is a 2-dimensional surface, and 2 is its intrinsic dimension. It means that if we are on the torus, we are on a 2-dimensional surface, just like if we are on the globe, we are in 2 dimensions on the globe surface, on the Earth surface. Yes. However, there is also the space, the 3-dimensional space that is required to create this, to recreate this torus correctly without squashing it, is called the embedding dimension. Yes. So these points are in 63 dimensions. This is the ambient dimension. This is the original dimension of the data. We map all the data to 3 dimensions, but inside these 3 dimensions, there is a 2-dimensional manifold. I'll return to this. Now that you saw the data, let's see what we do with this data. So let's look at some manifold learning algorithms. And there are very many manifold learning algorithms. They all start in the same way. And I'm going to describe in this talk just 3. But I hope that if you listen to the end, you are going to be convinced by me that you only need 1. And it pretty much doesn't matter which one. There's a whole class of algorithms that you could use, but you don't need all of them. You need just 1 algorithm. And that's because of the metric manifold learning. However, before getting there, let's look at this toy data set that contains points in high dimensions. Again, it's a surface embedded in some very large dimension. This is the input to every manifold learning algorithm. And immediately as we get this data, we choose a value epsilon, which is the value that's called the neighborhood radius. And the neighborhood radius is the distance between points where we can assume that the points are nearby. Yes. So we would like that these points be neighbors, but these points across the dumbbell not be neighbors. So we would like to choose the epsilon so that we capture the scale where the local neighborhood. Yes, so that when we create the connections between neighbors, everything that is not connected are points that are actually connected only through the other points in the manifold, so that their global distance doesn't matter. And after we create this neighborhood relationship, that's essentially a graph. And the graph will be sparse if we did our construction correctly, because if it was dense, if the points from here would be connected to the points from here, then everything would be basically squashed in a big ball, and we could not see the local structure. Yes. So by this graph, we actually are marking what is the local structure around every point. What is happening, who are the neighbors of every point. And after we do this, then for the pairs of points that are neighbors, we calculate the distances. And we create a matrix that contains these distances and is sparse in the sense that for the points that are not neighbors, it contains nothing. It contains infinity, essentially. But of course, we can't put infinity in a computer. And I hope you followed up to here, because this matrix is extremely important. This matrix contains all the information from the data that we are going to pass on to the embedding algorithm. So no matter what embedding algorithm we have, no matter what kind of coordinates we have and how many, all we need from these coordinates are their distances. And from the distances, we only choose the short distances. And that is what we pass to the manifold learning algorithm. And already knowing this, we learn what we are going to preserve. Because if we only have local and short distances, it means that all the other distances are irrelevant. We only want to find the structure that emerges from basically interactions that are local from neighbor to neighbor. So one can navigate through all this manifold and discover its topology and discover a lot about, so the topology means how, if it has a hollow in the middle, if it has holes, if it's flat like this piece of paper. Yeah, we can discover all this just from the local connection inside the neighborhood. So let's see how. Optionally, and this is going to be this is going to happen in the algorithms that I'm going to describe further. From the distance matrix, we'll construct a kernel matrix or a similarity matrix by taking taking basically a Gaussian function of the distance. Yes, and so now when a distance is large, this Gaussian is close to 0, but the distance can't be very large. Yes, and when the distance is close to 0, this is close to 1. The diagonal is here blue because we ignore the diagonal. And then everything we are going to do is on this matrix or on the similarity matrix or on other matrices that are derived from these matrices, and they have the same sparsity pattern. So in other words, on the points that are neighbors, on those edges between points that are neighbors, we perform some calculations. Yes. So this is what every algorithm does, and now we are going to see further on, what do they do with this matrix of distances? By the way, this matrix is the dimension of the data set. So there are n points, so this dimension is dimension n. Here is one of the oldest and simplest and very still useful algorithms. It's called isomap. Once we have a distance, a matrix of distances, we can actually go from neighbor to neighbor and find the shortest path distances in the graph. And this matrix is going to be a full matrix because between every 2 points you are going to have a distance, but it's the distance calculated in the graph. Yes. So if we were here and we wanted the distance between this point and this point, it wouldn't be the distance through space across, it would be the distance around the dumbbell. Yes. And then they apply an even older algorithm, an algorithm called multidimensional scaling. And I expect that some of you have heard of it, which actually finds coordinates for points that preserve this, this set of distances. if you happen to know multidimensional scaling, you will know that the way they find the distances is by doing an eigendecomposition and taking principal vectors of this matrix of a matrix derived from the matrix of squared distances. And this will be a common theme. Whatever we do, and I'm going to show again this primal matrix that starts everything. From here on, we are going to do something that will remind you of principal components analysis. And principal components analysis is something that everybody uses. In some sense, manifold learning imitates it because many of the methods that I'm going to describe also take eigenvectors, principal eigenvectors of a matrix derived from this matrix of this sparse matrix of distances, but in some ways it's not. And the reason it's not is partly because this matrix is sparse and reflects nonlinear structure. And the pre-processing that is done with this matrix, which is extremely important. That's actually the core of manifold learning. Differs from algorithm to algorithm, and is much more complex than what is done with principal components. However, in the first approximation, you can think of the similarity, the fact that we always look at principal vectors of a positive definite matrix. Okay, so let's see algorithm number 2. If you want to use a single algorithm for manifold learning, this is the one. And you will see why. The reason why is because it's based on the Laplacian matrix, and the Laplacian matrix is extremely important for other reasons. It carries in for other information, more information than this algorithm can use. And so because this algorithm already calculates the Laplacian matrix, you can just as well use this algorithm for the rest of, for the embedding itself. A matrix from the similarity matrix that I showed S, another matrix L is computed, and we take its principal eigenvalues, which represent the coordinates of the points. Just like the principal eigenvectors of, in principal components, give us the coordinates of the points. So we have column vectors, and the rows of the vectors represent the new coordinates of the low dimensional coordinates of the points in principal components. In the same way, here the eigenvectors of L are some column vectors phi. The first one is discarded because it's a constant, or in any, it carries other information than about the geometry of the embedding in any case. And then the rows of this entry I in each eigenvector is a coordinate for the new points. And what you see here is another torus that represents another molecule, another small molecule. You are going to see various organic molecules, small organic molecules scattered through this talk. This is the molecule of ethanol, and it's also a torus because it also has rotation components. And here again is the definition that I talked about. The intrinsic dimension is 2, and is the number of degrees of freedom, and the embedding dimension is 3, which is the number of dimensions that we need to be able to correctly, to embed this shape without squashing it. Okay, let's see if there are any questions. I have 2 more slides from this chapter, so feel free to enter your questions while I talk about a few more things. Here is a third algorithm. This is a much more recent algorithm called UMAP. And I'm going to type the names because I apparently didn't put it here. There is a very well-known and very popular embedding algorithm called Tisney, and there are other things called autoencoder that I'm sure you've heard of too. I want to make the difference between these algorithms and the previous ones. These also produce low dimensional embedding, and autoencoders are tremendously useful, but they are not manifold learning algorithms in the sense that a scientist would like to use. And by the end of the talk, I hope that I'll be able to explain this better. I consider UMAP and TISNI mostly as heuristics that gives us a visualization of a quick visualization of the data, in the sense that they take data and spread it nicely on a table, keeping some of the local structure so that we can see something. However, the problem is, what do we see? And my hypothesis, what I would like to say, is that probably we only see what we know in these data. Yes. If I was to give a more formal explanation of what I just said, with only see what we know, is that these algorithms are much harder to analyze. Let's put it in the fact that I don't know anybody who analyzed them properly, whereas the algorithms that I just described, like diffusion maps and isomap, have proof of consistency, so we know what they do. And as I hope to show, if I have time, this will be pretty important. This is a slide about the construction of the famous Laplacian matrix. I'm not going to expect you to read it. I want you to see that it's just all matrix computation, but what computations are there is extremely important. And once in a while, I'm going to highlight seminal papers in this field. Koifman and Lafont 2006 is one. They showed why the calculation of this particular Laplace of this matrix has to be done this way, and metric manifold learning, in some sense, couldn't be done if this Laplacian would not have been defined, and they would not have proved the construction of this matrix. I know that this is vague, but the next slide will explain a little bit better what I mean. So the next slide is an overview of something that I don't know if is perceived enough. So I'm asking, why is manifold learning hard? But lots of people will say manifold learning is not hard because we have TISNI and we have perhaps Laplacian eigenmap or isomap, and they do the job very well. I disagree, and then once in a while there will be a slide to explain why. In more concretely. But here at the highest level, there are three things that can go wrong and will go wrong. At the bottom one is that the intuitions fail us. And they fail us because our intuitions are very linear and very tied to the three-dimensional space where we live in. And manifolds, even as soon as we are in 4 dimensions, have so much richness that even experts, mathematicians, and I don't even consider myself an expert in manifolds. I'm an expert only in manifold learning, which is a small part of differential geometry, if it is at all. Even experts are not sure how of all the possibilities that the nonlinear smooth world of manifolds offers. So we should not rely on intuitions. We should always, it's important to use statistics to prove that what we do is correct. And what do I mean correct? Again, I will elaborate on this later. But what I mean correct is that the algorithm doesn't produce artifacts, so that when we see something, what we see in the embedding is something that we see in the data. And that is important for science, because you do not want to see patterns in the data, in the embedding, in the low-dimensional embedding that were not in the data. We want to draw scientific conclusions from the data, so we want something that is faithful to the data and not invented by the method that we use to embed. The first reason is that manifold learning is not parametric. And I don't expect many non-statisticians to know what non-parametric means. But if you are familiar with kernel regression or kernel density estimation or spline regression or support vector machines, these are all non-parametric methods. And one thing that differentiates them from models like mixture of Gaussians, which are parametric, is that you need much more data to obtain accuracy. Why? Because these models are much more flexible. And we need flexible models in order to match the richness of the manifold world. And because these models are infinite dimensional, which means that with enough data, they can fit any manifold as complicated as it is. However, because they are so flexible, they need much more data to get the accuracy. So you all know that the variance sigma squared decreases with 1/n, the sample size. Which means that if you want to increase the accuracy of estimating the mean, by a factor of 10, you need 100 times more data. I hope this makes sense. Now, if you want to increase the accuracy of a manifold estimation by a factor of 10, you need an exponential factor more data, and this is exponential in the dimension. So for dimension equal 2, that's not so bad. For dimension equal 4, it starts being difficult, and for dimension equal 10, it's scary, and perhaps we will never have enough data to estimate accurately a manifold of dimension 10. And the third reason ties with the fact that our intuitions are not correct. Because manifolds are curved, and because distances are somehow stretched on manifolds, and we'll talk about it, I'll get to it in the next slide, errors don't average to 0. So when we estimate something, we can't believe that if you just get more data and do the sensible thing, we'll get the right result. That's not true. We'll do what seems sensible and get more and more data and keep getting the wrong result. And that's why we need statistics, because statisticians and geometers work very hard to compute the limits of the things that we are doing to explain what is the correct thing to do. And this is actually the importance of this paper. They said, no, this normalization is not enough. You need another normalization, and this should be it. One could not have guessed this by trial and error. Aha, I see a question. If the non-RBF Gaussian kernels used to compute Laplacian, the answer is that in theory, we can use any smooth kernel that decays fast. So a triangular kernel is just fine. Yes, a triangular kernel is just fine, but the triangular kernel has a sharp, is not differentiable, and the sharp corner would not be okay. Yes. However, what we do is first we compute a neighborhood graph, and then we truncate every kernel to, so this Laplacian is always sparse because we compute the neighborhood graph. So it's not, the choice of the kernel is not a problem, just like it's not a problem in kernel density estimation. Thanks for the question. Oh, I see another question. No, the kernel is just like in kernel density estimation. It doesn't really matter. At least not in the infinite sample size. So it better be smooth and decay fast. Okay, so I said that there are many manifold learning algorithms, and here is an example. So this data set is just a sheet of paper, the one that I waved before. It's this sheet of paper that was rolled in 3 dimensions. And the task of manifold learning is, of course, to say, oh, this is 2-dimensional. And in fact, because it is a sheet of paper, I can make it flat into 2 dimensions. It's like a very, very simple problem. And the only trick is that I add a hole to it. Yeah. And here is the isomap algorithm. And here is the Laplacian eigenmaps diffusion maps algorithm that I boasted about. And here are 3 others. And I hope you see that there is a problem here. Right? Actually, there are multiple problems. First of all, each of them gives a different embedding. So if Sheridan goes and uses isomap and says, aha, my reviewing data looks like this. And Michael goes and uses LLE and says, oh, no, the same reviewing data looks like this. It's clear that at least one of them is wrong. Like this, or in the best case, and that's actually the reason, like that's actually something that we'll conclude later, both of them are right, but they can't talk to each other because these data, these results are not reproducible. And if a third person takes a same different data set from the same distribution, they might get a different embedding again. So this is clearly not a way to do science. Notice also that here we know what the answer is. And none of them is the answer, right? In some sense. But if we had a spectrum of galaxies where we don't know what the answer is, this is actually basically a catastrophic problem. We could not do manifold learning if we couldn't solve this problem. And before I explain how to solve it, let's look closely and see if all these are wrong in the same way, or maybe if they are right in various ways and wrong in others. First, let's look at these two. These two, take the manifold and kind of glue it together. This is clearly wrong because it brings together points that were not together before. So these do not preserve the topology, and we cannot use them. This algorithm, Laplacian eigenmaps, in this case, does preserve some of the topology because it keeps the whole. However, makes the data one-dimensional when the data is really two-dimensional. This is a minor mistake. Ask me later, we are almost out of time, so I want to go on a little more. Ask me later, what is this mistake? Because we have, my group has an algorithm that can correct it and can make a good embedding from this. Yes, and notice the horseshoe shape. Whenever you see this horseshoe shape, it means that you could do better, that your algorithm did almost perfectly, but you don't know it, and you could do better. But between ISOMAP and LTSA below, the difference is one of deformation. So both of them get the topology perfectly, but with respect to the original data, which is this, they distort it, as if it was this. Yeah, and this is actually correct because a manifold is, by definition, if you know the definition of manifold, is supposed to just be a stretched form of the data that was. So it's our notion of correctness that is lacking, it is not completely defined. So to go back, if we go back to mathematics, we get a mathematical term for what is happening there. If the mapping from the manifold to phi of m, which is the low dimensional embedding, is what's called diffeomorphic, it means that it preserves topology, which means that it keeps the neighbors that were neighbors in high dimensions, also neighbors in low dimension. It doesn't break them apart. And it doesn't put together neighbors which are not neighbors before. And that's easy to satisfy in practice. But what we want is something more. We want it to be an isometry, which means that we want also to find the same distances if we measure them in low dimensions, like here. And we want to also keep the angles the same, keep volumes the same, and so on. And for a long time, people developed various algorithms, some that preserve distances, like ISOMAP, some that preserve angles, some that preserve other things. But if you look in a math book or ask a mathematician, you'll learn that there is a way to preserve all of them in the same time. And that's the notion of isometry that Riemann invented. So based on what Riemann invented, my student Dominique had a very nice idea. He said that if you want some mapping of the data to be equivalent to another geometrically, then it's not enough to have the coordinates. You have in each point to have something called the Riemannian metric. And so if you want to correct the problem that we see here, it's not enough to, you can just as well keep these coordinates, but add some more information which tells you how they were deformed with respect to the original, their original relative position in high dimensions. That's the idea. And now let's see how this goes again on the faces. Yeah. So this is the original, this is the embedding that I showed before, the two-dimensional embedding of the high-dimensional face images. This is another embedding. That one was by ISOMAP. This one is by LTSA. You see that the coordinates are different, but in each point on the coordinates, I attach a small ellipse. And this small ellipse represents the Riemannian metric. What does it tell us? Let's look here at this corner. Yes. Obviously, the points here are too stretched. Some stretching happened. They shouldn't be there. They should rather be here. Well, if we go along this ellipse, we see that they're very narrow. So when we go along this direction, if we multiply the distance that the distances with locally with the width of this ellipse, this width is the correct multiplier that corrects the distance and brings it to what it should be. So this narrow ellipsis tells us that this distance is not long as it should be. It should be divided by a factor of 10, yes? And here when we go along this direction in the manifold, we see that the ellipses are elongated. So here the ellipsis tells us that if we go into this direction, the distances are longer than they appear. Yes. And of course, because every place is stretched differently, at every point we have an ellipse that tells us what is the local deformation, and moreover, what is the local correction that we should make. So we are okay to have any of these two, because each of them has its own ellipses that, or Riemannian metrics, that describe the local correction. And even this one, although this has a topological singularity, let's say. Yeah. So the ellipses all describe the local correction. So it doesn't matter what coordinates we use, because if we want to calculate the distance between this point and this point, which is this point and this point here, probably, we'll always get the same distance as long as you apply the right correction. I hope that this makes sense. And I'm going to skip the formulas. Here is a proof by experiment. We have this nonlinear, this hemisphere, and I don't know if you can see it, but on it there is a quarter of a circle. So a quarter of a circle is pi over 4, distance is 157, with several embeddings. Here are the embeddings. Here are the uncorrected distances. Here is another set of uncorrected distance, the distance of the segment. And here is the formula that you should use. And this G is, as I explained, is the correction applied from the Riemannian metric, from the ellipses. Yes. And once we use the correct distance, we have the blue column. And in the blue column, the distances are all the same. There is an error, and the error is due to the curvature, because the distances are measured as along a circle. But as you see, every algorithm gives us almost the same distance. Yes. Okay. And I think that I'm almost close to stopping, but I want to highlight something else. And for this, I like to show you the picture again. So in this picture, not only we know how to correct the distance, and we will know that if we go this way, we have to correct the distances by multiplying them with a small number. But it suggests to you, I suppose, that this can also be shrunk, right? It's an elastic, it was pulled. We can maybe invent an algorithm that relaxes it back and makes it correct. And that is true, and we did that. And this is called Riemannian relaxation. And I have only this slide about it. This is the ethanol molecule in alcohol. This molecule is so small that even if we do principal components, we can see the shape of the torus. However, it's hazy because there is still noise in this data. This is the embedding, and it is misshaped, and the misshaping has to do with the high density regions here. So when the density is higher in manifold learning, you're going to see these corners appearing. Yes, and when the density is lower, then the manifold expands. Yes, that's why instead of seeing a nice torus, we see a triangle. Yes, and this just measure the red and blue are extreme distortions. Yeah, so this is what we get if we apply diffusion maps. But if we apply RR, which is Riemannian relaxation, our technique, then we create a torus that looks like a cylinder. So it's similar in shape to the original one, but it's cleaner. It's smoothed data. So it's better both in this and then this. And here you see that the distortion is close to 1. Yes. So to summarize the chapter about metric manifold learning, we can measure the local distortion that the algorithm creates. This doesn't depend on how we obtain the coordinates, what algorithm we use. It applies to any algorithm we have used, as long as the topology was preserved, as long as the neighborhoods were correct. And once we do this, it doesn't matter what algorithm we use, because we can compare the output of different algorithms, since we have the intrinsic distances between the data, good approximations to the original distances between the data. Yes. I'll talk about the applications in the next slide. Now, I want to show you the manifold learning sandwich. So what is the sandwich? Well, the meat is in the middle. This is the manifold learning algorithm. And I hope that I convinced you that if we use metric learning, then it doesn't matter what algorithm we use, because we always can do the correction inside the computer with by computing the Riemannian metric. So in the middle, it doesn't matter what we put. This is not the same as a real sandwich, right? In a real burger, you really want to know what meat you are using. But in manifold learning, it doesn't matter what you use, as long as the topology is preserved correctly. However, what matters a lot is what you put before and after. Yes. And why this matters is because if these things are not correct, then we are going to get things that do not correspond to the real manifold. We are going to get artifacts. And I'm going to use a couple of minutes to show you what kind of artifacts. But what are so we have to make the right choices in each of these steps before, and then we have to actually get information from the data. Unless it's two-dimensional or one-dimensional when it's easy, we have to do more post-processing to extract the information correctly. Yeah. But more importantly is to actually run the algorithm correctly. So we have to do these steps correctly, the pre-processing steps. What the distance measure this is, I'm going to skip this. If you use Euclidean distance, but most people use Euclidean distance, but if you have complicated things like molecules or other things that are not really vectors, then you have to think of the distance. What graph construction? I'm going to show something next slide. What bandwidth means how do you choose the neighborhood radius? And that actually has a very important, an influence on what you see in the data, because you are choosing the scale at which you look. Yes. Then you have to know somehow what is the intrinsic dimension. And that's because you need to know how many free parameters are in the data, how many degrees of freedom. Yes, this is the science in the data. This is understanding the data, to know how many degrees of freedom, even though it may not be necessary for just looking at the data. And then you need an embedding dimension, and this embedding dimension has to be sufficient so that these many degrees of freedom can be mapped without squashing. Yeah. Now, after you produce the embedding, you can find clusters, as I showed. You estimate distortion, and that's done by metric learning. You can do something that's called independent eigenvector selection. And you can do something that we did recently, which is called the meaning of coordinates. Yes, and this is actually the same list, but with bibliographical references. Yes, and this is a picture of the same list or similar list, which shows that not only all these are necessary and that we worked on them and we have solutions for them, and some of the solutions are pretty good. All of them are implemented in MegaMan, but that many of these solutions are based on the Riemannian metric estimation that I just showed. This is the Riemannian metric on aspirating. Okay, now I am 5 minutes from 9 o'clock, so I would stop. I will go to the conclusions, which are far down. Oh, I must show you this construction. Yes, so there are various things about, there are various ways to construct a graph. Some people say nearest neighbors, some people say all the neighbors within a radius. K nearest neighbors is by far more popular. Also, it's very popular to say it doesn't matter. But the truth is that it does matter very much. Yes, and here I show this. The purple is the ethanol embedding that you saw before. It's triangular, but let's not worry about it. And here is the same embedding without the second normalization. And perhaps it looks like we matched them to be about the same size and overlap as well as possible, but you can see that the corners are much sharper. Yes, and this is the K nearest neighbor graph. So we use the neighbors within radius R, as I said. If you use the nearest neighbor graph, this is what you get, something extremely non-smooth. In fact, you can even go as far as finding clusters where there are no clusters. So here is the second seminal paper that I want to point out, Hein 07 and collaborators, who showed this effect. They showed that it's important to not use the nearest neighbor unless you really want to find clusters in the data, even when there aren't. Yeah, I have a lot to say. In fact, I have to say something about directed embeddings, but I also want to get to the conclusion. And I have two kinds of conclusions. One is that manifold learning should be like principal components from the point of view of the scientists who use it. Yes. And by this, I mean that principal components is reliable, it's tractable, it's scalable, and it's automatic, which means that you always know what you get. And that's why you can use it as first step in data preprocessing pipeline because you can trust its output. And then this output is fed to various other algorithms, perhaps it's used to make scientific discoveries on its own. But whereas manifold learning very often these days is still used for as the last step. We map the data by manifold learning and then you look at it. That is not fair to the scientist, essentially, because that means that the manifold learning algorithm gives the scientist something that they are supposed to evaluate by themselves. They're supposed to do more experiments to see if what they see is true. They're supposed to actually see if something is wrong. And that is not a recipe for discovering what, that's fine to confirm something that you already know, perhaps, but it's not a good recipe for discovering something that you don't know. If you want to discover something that contradicts what you think you know, then it's important that the algorithm that discovered this be reliable and trustworthy and reproducible. Yes, but there are also intrinsic and mathematical reasons why manifold learning is not like PCA, and that is because manifolds have a much richer structure and there is much more to estimate and to find from them. And now I will stop and see if you have questions or if you have basically would like to see in more detail some of the things that I skipped over. Michael? Aha. It's a good way of putting it. Yes, in some sense, yes, it's a very good way of putting it. One other way of putting it is that nearest neighbors try to make the density uniform, even when it's not. And for some strange reason that is actually takes proof, it forces the data to break into equal parts. I could.
Yeah, I mean, that's kind of what I was thinking. Is asymptotic is kind of what's going on there, like growing neighborhood versus not growing neighborhoods, and like you said, uniform versus
even with K and N, if you want to do it right, you don't keep the K fixed.
Right, exactly.
So basically, yes, in the most visible papers and prominent papers, K is fixed to 5, but that's not what you should do. Asymptotically, one has to increase K at the correct rate. But even so, there are biases.
Okay.
And in particular, with the K nearest neighbor, we don't know how to estimate the Laplacian. Yes, so to do metric manifold learning, we need to have a correct unbiased Laplacian. And the one working method, so it's not impossible. It's not that you can't estimate a correct Laplacian with K nearest neighbor. It's just that you have to divide by the density, and that's very, I will divide by something that could be near 0. For instance, whereas with the whereas the really well-tested Laplacian estimation by the diffusion map, the Koifman and Lafont paper that I mentioned, gives us the correct Laplacian, so then we can get the metric correctly. That's another reason. Because as I said, it doesn't matter what algorithm you use. So you could use a KNN graph, just that you would need the Laplacian anyway afterwards.
So can I ask thank you so much. That was great. One of the questions that I have is related to what was on the previous slide, which is to some extent about interpretability. I mean, so many people are familiar with PCA and factor analysis, you know, these kind of matrix factorization techniques in a general sense. And one of their most kind of useful attributes is that interpretations are quite often, they're both familiar, but they're kind of easy because it's you know, it's a linear situation wherein you can look at something even as simple as like the correlation basically, or just the overlap between a component or a factor and an observed variable.
Mm-hmm.
And then obviously when that overlap is high, then you can attribute some substantive meaning to the factor or the component that is related to the substantive meaning that you're giving the observed variable.
Mm-hmm.
And so that kind of sets up two issues there. And one is, how can we measure the kind of overlap between any given observed variable, you know, or dimension in the data, and what gets kind of, I don't want to say extracted, but the underlying, but the dimensions produced by a manifold learning technique. So how do we provide an interpretation to those as well, I guess would be the second part. So,
I thank you for this question. Are you sure you did not prepare it just to please me?
No, I'm wondering myself.
This is the last thing that on my list. It's the, it doesn't have a title here, but it's the coordinates with physical meaning, or I could say real meaning, and it goes as follows. So here is a manifold, it's ethanol again, it's a different embedding, it's even more triangular, but it doesn't matter because we correct it always, okay? And you see that ethanol has these three, like has two joints, right? And so because it has two joints, there are two circles, two angles of rotation. And if you color this manifold by the yellow angle, you get this coloring, which just shows that the yellow angle goes horizontally. And if you color it by the purple angle here, then you see the rotation goes vertically. So just like in principal components, you can plot this. If you have good guesses of what is going on, then you can plot these functions and see them on the manifold. And in fact, this also tells us that of all the, like, basically, it's not the vibration of a single molecule, but there are these particular angles of rotation. So this is science in some sense, and a very low level, yes? These particular angles of rotations are what governs the long range important movements of the molecule. So if this was a protein, this would be protein folding that you'd be discovering. I'm not saying I can discover it with manifold learning. That's a very difficult problem. But this is what you would be discovering by just plotting these. However, if the molecule is only a bit larger, the number of possible rotations grows like n to the fourth. So there are way too many to try. So, and that is true possible if you have principal components and you have many functions to try. Maybe you don't have enough graduate students to try all the possible functions that, that could appear in a 5-dimensional component, PCA, yes? You need 5 things. Also, they are correlated somehow, so it's hard by the eye to discover which 5, yes? And so without boring you with the details, we have a method that could be that is for manifold learning, but could be simplified to be applied to principal components or to factor analyzers. That, and I will skip all the details, basically the end result is a lasso problem. It's called functional lasso or group lasso. And so if you solve this, basically, I don't know, I suppose you may have heard of the lasso, right? So it's a regression with a penalty that makes the sum of the coefficients be 0. So it's a linear regression with some coefficients forced to be 0. And there's no time to explain why we get a linear regression, and that is the correct formula. This is not, we did not force something into linear regression. We did we found a natural linearization of the problem that makes the problem be linear regression. And if you solve this problem, then you can select from a set of, here is a very simple older example. We have 4 functions, and our algorithm selects the 2 which are the correct ones. Yes, and it also tells us that the first 2 coordinates are described by the purple one, which is this, And the third one is described by this one. Yes, so this could be applied both to manifolds and to principal components, and it's a method that, without being a silver bullet, it can select from a largish number of possible candidates the functions that actually parameterize the manifold. Yeah.
Okay, great. And then based on that regression approach, you can derive both substantive meaning as well as a sense of, so a meaning of the kind of factors. I don't want to call them factors because that I think that implies linearity, but a substantive meaning for, yeah, go ahead.
Okay, so I want to say you can have like 100 candidates factors, but you need only 2 because there's 2 dimensions, so there can't be more than 2 independent ones. Yes, and so what you do is you put all the 100 independent possible factors in your problem, and the ones that will have non-zero coefficients will be these 2. That's how it works.
Right.
Sorry to jump in, but I guess the question maybe is like, how do you know that those 2 factors correspond to rotation, right? In a general problem.
Oh, because
is that kind of what Michael's asking?
So in
To
a
some extent.
this is a method for scientists. So scientists have good guesses about what would be interesting functions. Yes, like scientists in chemistry know that these torsions, that are called these high-level rotations, are good candidates, but there are just too many, or it's much faster and more reliable to do it by computer than by looking at them. And you couldn't actually look at anything that's more than 3 dimensions. You'd have to, invent other methods. Like, yes. So this just automates what scientists would do, adding also. So letting you add more things and doing it faster.
Okay, so the scientists know, this molecule is going to exhibit some rotation properties, but like, I just don't know which, and I know that this behavior is nonlinear. So what I want to do is just chunk all of those potential rotation properties into this.
Yes, exactly. Yes.
Well, I want to learn them, and then I want to chunk them into the lasso to pick out the ones that are actually visible in my data.
Yes, yes. Or suppose you have something like some social science data set, you can put the demographics like age, gender is not continuous, so you couldn't put that, but age, state of health, geographical location, everything that's continuous and has a derivative. You could put all of them in, and the power of the method is that they don't have to be separate coordinates. It could be age squared times income. Of course, that's silly from the economic point of view, perhaps. But if that's what describes your manifold, then you're going to find age and income.
Gotcha. Yeah, that makes sense.
So that's interesting. Sorry, I don't want to, if anybody else wants to jump in, please do. But just as kind of a follow-up, so again, drawing analogy to traditional linear techniques, one of the things that we often do when we're extracting factors is we might not force factors to be orthogonal to each other, right? So we allow for non-orthogonality. And I'm just wondering here, so if we take this example of the molecule and we have rotations here, does this approach kind of, I don't want to say force, but just by virtue of the Laplacian and the operations performed on it, are we kind of assuming that the rotations are independent?
They have to be independent, but functionally independent. So so the trick is as follows, and that's just comes from remembering your Leibniz formula. When you take derivatives, if something is a function of something else, their gradients are linear combinations of each other. Yes, it's here. Yeah. Okay, it's not quite. Yes. So basically, if phi is h composed to f, and this could be any nonlinear functions, then their gradients are in a linear relationship. So instead of solving a nonlinear complex system, you turn it into a linear system with like m coordinates if you have m vectors, a larger linear system. And so it means that locally you have to have a basis at every point. The two gradients have to be linearly independent, but they don't have to be orthogonal. What happens if they have too many things that are close to each other or dependent, then you start getting collinearity. And it's the same problem as like collinear covariates in regression. If you start having that, then it's harder to choose. For the same reasons that it's hard to choose in regression. So you could, you haven't gone that direction because that's a very well explored area, but whatever people do or can't do in plain regression, when they have covariates that are too close to each other, it's the same here, except that it's in a nonlinear world, very, very freely nonlinear.
How fast are these algorithms? Sorry, go ahead, Howard, go ahead.
Just to kind of think about, so the Fs here are the individual possible representations, right?
The Fs, yes, the Fs are the covariates that you put in, the features that you are interested in.
So the feature, so in this case, the features are the possible representations that you're talking about?
No, just like things like age and income.
Okay,
and
so they're actually.
Yeah, your own interesting functions, whatever you want.
Okay, and then.
And phi is the manifold, is what I discovered by manifold.
So phi is the manifold, and so basically some function of these features creates the manifold. So that's what this. Okay, so yeah, I just wanted to get a better handle on what the notation was representing.
We have another new version of it that's submitted, but essentially the idea is the same.
Okay.
Yeah. By the way, thank you, Sheridan, for sharing the links. Yeah. Okay. I can stay a few more minutes. Like,
okay.
Like I said, people can jump in, but people can jump out.
how fast? Sorry. How fast are the algorithms? So Mega Man, for example, do you have a sense for how fast it is in with different numbers of dimensions and obviously as the quantity of data?
Okay, so great question. So after you compute the neighborhood graph, the ambient dimension is gone. And that's actually a fairly expensive step because you have to compute. If you're smart, you don't compute n-squared distances, but it could be n-squared. You always need large data. But to give you an idea how fast, I keep trying to tell my students to work on the cluster, and they keep keeping 50,000 points and working on their laptop. So they clearly can write lots of papers with 50,000 points limit, more or less, or 10,000 points on their laptop. Those million data sets, we benchmark them on a single core on a desktop 10 years ago, maybe, and it took a few hours, like a couple of hours, maybe 3 hours, 4 hours per minute. Now it will be much faster. But we don't have so many data sets with 1 million points. For this functional lasso, it turns out that you don't need the whole manifold. So we pick a sample of 50 points. Now, if you picked 100 or 1,000, you'd get more accuracy, right? Because you had more points. But you do it with 50 points, it's a matter of minutes, seconds.
Right. In that case, this seems like a potentially very useful way of almost like a pre-processing step if you wanted to carry out additional analyses using the extracted dimensions or factors. Because you would get a kind of manifold or geometry sensitive denoising to some extent, right? Just like you normally do with factor analysis, for example. And then if you can take the dimensions or the factors that you've extracted as data, then you can do all kinds of things with them afterwards.
Yeah, exactly. It's a denoising method. Manifold learning is a denoising method.
Right.
Just to advertise, actually, I'll put the slides on the web as well. Before this, I have this embedding of graphs. And that shows what to do if you have things that are a graph that's asymmetric. So in the job market, people enter the market and maybe they exit it, but it's not distances between jobs are not symmetric because it's one way to go from waiter to teacher and the other way to go from teacher to waiter. So much, it doesn't happen so much. And so you can't model them as just points in space. So if you want to see the space of jobs, which is what I described here, you have to assume that there is also some flow or something pushing the people to go in a certain direction. And we have a method that can do that too. This is actually the first work of my student Dominique 10 years ago now. Yes, so it can actually take a graph and separate what is the geometry of the space and what is the flow on it. But maybe I should. Maybe.
What is this? What is this called? What's the method called?
It's called directed graph embedding.
Directed graph embedding.
Actually, I should probably go to the bibliography slide here. So, and it's not here.
So is that
manifold with vector fields? Yes, here.
Okay, right. Is that useful for finding? I mean, one of the things that we're wondering about too with my colleagues and some of the work we're doing is how to take a manifold. And so, for example, if you whether through dimensionality reduction techniques or whatever, get information about a manifold and then interrogate that. So for example, uncovering attractors, attractor basins, separatrices, and then based on that information, you know, using kind of location sensitive or making location sensitive predictions. They could be probabilistic, obviously, about, for example, switching between different attractors or attractor basins on a manifold. And the minute I see something that looks like a vector field, then I start thinking about that. What
so
is that?
Actually, I'm getting more and more interested in dynamical systems. So this is just the precursor because this just assumes that you have a graph. Right. It's a very simple method, but if you give it a directed graph, it will give you the vector field and the continuous space where it is.
Right.
However, all these methods give you just points in space. So you have to figure out that there's an attractor there. So it doesn't finish the story in some sense. Yeah, it just gives you the points in a better denoised.
But then you can do something, various things, clustering.
So yeah, so the idea is that if you do it right, then whatever you would have done with the full data, high dimensional data, you can do with the low dimension, and better because it's denoised. This is in the worst case, but you can sometimes very often do more. In fact, we have now a paper that we are preparing to submit that is on the so Laplacian eigenmaps is eigenmaps. Yes, we are doing eigenflows, and so we are getting the decomposition into harmonic flows and rotational flows, and so we are getting closer to what you want. So if you ask us in a year or two, or if you want to collaborate, then we may do it faster.
Yeah, definitely. I mean, obviously in the health and social sciences, we're often working with what we assume to be dynamical systems, and we often have longitudinal data, just like the what was it, the NLSY or
longitudinal survey of youth in the United States.
That's right. That's right. So we have, you know, kind of a variety of data sets, both high and low throughput. We get them all the time, right? If you're doing EEGs, for example, you know, you're sampling at what, like 5 kilohertz or something, and you have tons of data, but it's in high dimensions, and so you need reduction, obviously there, but then also you're interested in, like you're saying, dynamical flows.
Yes, yes. Actually, that's very interesting data. I haven't worked with it, but it's both fascinating and hard, and kind of it looks like it's within reach somehow.
Yeah. Okay. Should we call it a day? What do you think?
Okay, good night. or
yeah, right. Exactly.
I'll stop recording now. But
okay. Thank you very much, Sheridan, for being here for us and recording.
Yeah, no worries.
Thank you.
Thanks.
Yeah, absolutely.
So I will post this, or I and Sheridan